sessions on single learnings. So for this session, there are totally 4 this work will be presented in these sessions. And for each presentations, there will be 12 minutes for oral presentations and 3 minutes for Q&A. So now let's invite Mr. Philip Tannor to present his work. AugBoost gradient boosting enhanced with stepwise teacher optimizations. Let's thank the speaker.
Hi, I'm Philip Tannor. This is a paper that is part of my master's thesis. I'm from Tel Aviv University in Israel, and Professor Lior, this was joint work with him. He's from University, which is also in Israel. It's called AugBoost, and I tried to improve gradient boosting. So let's do some introduction. Who here, raise a hand if you know how to explain how gradient boosting works. All right, that's great. Not a lot of hands. Gradient boosting is used very commonly. It's implementations that are the winners of most casual competitions that aren't neural network based. And not a lot of people know how to explain it because many of the original papers that discuss it aren't very explicit or very clear about it. So in this slide I'll explain a bit how it works. So here we have a toy case. Let's say the label is the age of someone. We're trying to predict his age based on these features. So we start by training a decision tree, let's say a regression decision tree. We get predictions, but these predictions are a bit off. So if we subtract the labels, the original labels, we can get a residual, and now we're going to have a sequence of decision trees where each one learns the corrections, which means the residuals of the ensemble that's being created. So the next phase I create a new decision tree, while the target this time is the residual from the first decision tree. So then the next time I try to predict the residuals, you'll see they're also a bit off. And then I get the new residual, etc. So how do I get my final predictions from here? I basically, I'll simplify a bit. You just add them one to another. And when these corrections become smaller and smaller as the ability to predict becomes better, the sum of it is supposed to converge towards a fairly good answer. Now I simplified a bit. Really, it's not just the sum; it's a weighted sum. These weights are calculated during training, and subtraction is actually the gradient of the loss. So in the case of MSE, let's say it's really equivalent, but this is the general case. All right, so here's the same thing in pseudocode. I'll go over the highlights. So here's where we update the targets in each iteration. This is where we train the decision tree, and after we get the new decision tree, which is one of the weak learners, we add it to the ensemble. So hopefully that was clear. Now a bit more background about something else we're going to use. We use artificial neural networks for embedding, and I'll explain how we do it. So let's take the exact same case. So we train a neural network that the input is the features that you can see above, and the output is the label. So if this neural network trains well, now look at this last neuron over here. This last neuron somehow manages to predict these labels or the residuals with a good error. And if that's the case, that means that what it got from the layer before that, the one that's in green, that means that here there must be interesting information, which it's basically all the information comes from here, but it manages to facilitate this information to make a good prediction. So that means that if we extract the features from that last hidden layer, we may have refined information that will help us. So we'll use this later on. All right, AugBoost. Now we'll go into our work. So we talked about gradient boosting. We said essentially you have many iterations where in each iteration you create one decision tree. But we always use the same features. We don't change the features at all, even though the label keeps changing. But who said this should be the case? I mean, if the whole point of changing the labels and so forth is to, let's say, attack the samples that we're less good at, if you have samples where you keep, let's say in the case of age prediction, where you're off by 30 years, those are the samples we want to correct. So for those samples, it might help to look at the same information from a different angle. So here, now we'll show which changes we apply. So this is the regular gradient boosting. See, the original features are in blue, and the updated target for a given iteration is in kind of pink purple. So we train a decision tree based on that. And we add the decision tree valid ensemble, and at the end, using the residuals like we showed before, we update the training data. So here's what we add to it. What we do is we train the neural network as explained before, based on the original features with the updated target. So this is the exact same task the decision tree is going to see soon. And then when we extract the features as an output from the last hidden layer, and these are our new features. Now this could also be something else, we'll discuss it later. We can also augment features in other methods. So here we have the new features next to the old features, and with them together we train in the decision tree that instead of just using the original features in the regular gradient boosting approach. And this neural network, or whichever model we use for feature augmentation, we're going to store in the memory we use for inference. So the inference is fairly trivial once you understood the training. So here are the original features. We send them to the decision trees that we're training, one for each iteration. From each one of them we get predictions, and then the weighted sum gives us the final predictions. So this is classic gradient boosting, and here's what we added. We added the models that are used for feature augmentation. We get the extracted features from them, and we add this to and from this we get the new feature for the decision tree, and the decision tree has, let's say in this case, twice as many features as it would have had in gradient boosting. So let's talk about the augmentation methods. I mentioned that you don't have to use neural networks. So neural networks is a supervised method, but we also use unsupervised methods, which essentially means let's just, if we don't do dimensionality reduction, let's just rotate the feature space. I mean, let's keep the exact same samples, and all we do is change the axes and move them around. So this we did with both PCA and random protection without dimensionality reduction or without raising the dimension. We do something called augmentation recycling, which means I showed now for one iteration how you can augment the features by, let's say, training a new model. But what we do, we actually do this only once every few rounds, because for two reasons. One of them is for a better runtime, and the other reason is that gradient boosting, it really takes it a few iterations to exploit the new information it's given. This is a way to really utilize the information that's given to us in the new iteration. And then there's something that we were inspired by rotation forests to use. We don't create these augmentations on all the features together. We essentially divide the features into random subsets, and we apply augmentations on each subset differently. This is a way to generate more randomness that, as people that deal with ensemble methods can tell you, it's an important part of creating more diversity, which creates a more accurate ensemble. And for the case of, let's say, PCA, if I wouldn't have done this, it's completely deterministic, and we want the features to be different between the different iterations. So here's the pseudocode. It's fairly similar to what you see in the gradient boosting, and again, I'll show you the highlights. Here's where we do the augmentation recycle. You see only in some cases we create a new feature augmentation, otherwise we just take the augmentation from a previous iteration. Here's where we create the random feature subsets. Here's where we create the feature augmentation. And at the end, we add the new model to the ensemble. So let's talk about some of the specifics of the implementation. So we based it on scikit-learn's code base, even though it's not optimal, this was just simpler to work with. The augmentations don't change the dimension, which means if we started with X features, we create X new features, and there are 2X total features. And we concatenate them, as we saw in the diagrams. We don't just use the new features. The augmentation recycle we talked about, we do every 10 iterations. For these experiments, we create new features. We use 3 feature subsets for the experiments, and we use predefined parameters, which means we took the default parameters of the libraries we use, and everything we added default parameters, so there was no hyperparameter to it. So I'd like to mention AugBoost is similar work to what we did in our version of random projections, but with completely different implementation specifics, which means no concatenation, no feature subsets, and other implementation specifics at anything. But we'll compare to this as well during the results. So these are the results. these three leftmost columns are the methods we introduced. We compared to AugBoost that I just mentioned, and we compared it to the original gradient boosting. We also compared it to the IJCAI, which is a superior implementation of the code in gradient boosting. And I'll discuss what we saw. All of the AugBoost methods, everything we introduced was significantly better than when we started from the gradient boosting. So this is a significant improvement, and it was also significantly better than AugBoost. The AugBoost, the versions of AugBoost which use either neural network or ECA, were also significantly better than IJBM, even though it's based on an inferior code base. And something that's interesting about, even though this is work that we just re-implemented AugBoost because there was a code, but the AugBoost and IJBM have similar results, even though AugBoost, like ours, is based on the inferior code base, and that shows that maybe what they worked on was a step in the right direction. So, discussions. We can see that stepwise feature augmentation has a major impact, and I didn't show you these figures, but it seems that the main difference is the generalization. It's better at the test data, even if it's not as good as the trained data. And if different software implementations could further improve results, which means we base it on scikit-learn code, but if you base it, let's say, on IJBM code, you probably get even better results, and that's really the fair comparison if you want to compare with the same code implementations. There's a lot more to do, so let's discuss a bit about the future work. We used a simplistic artificial neural network. It was the same thing for every case. It was basically a few dense layers with the amount of neurons for exactly the amount of features. But you could use meta-learning techniques to pick the optimal artificial neural network, and that would probably improve results significantly. AugBoost with artificial neural networks, if we don't concatenate the original features, with the trick that we did, if we would just take the new features, then you can use it for complex data such as images. And maybe if you take the state-of-the-art neural network meant for image classification tasks, this could help you, let's say, improve on it. We took all of the features that we created and the original features, but you could apply features selection to only pick the best subset of features or close to the best subset. That could improve results as well. There are more feature augmentation methods to explore, autoencoder, Disney, LDA, and so forth. And every time we applied AugBoost, we used the same augmentation method in all the steps. But you could really alternate between them. You could do the first time an artificial neural network, then PCA, then go back to artificial neural network. So that's also interesting to observe when you try to create more diversity. And AugBoost on the regression task, as you can see, what we did was for classification. And to get good results for regression tasks probably requires at least better implementation specifics. So there's the code on GitHub if anyone wants to keep on the work. And if you missed anything during this lecture, then there's a blog post on Medium, which is fairly easy for you. And now I'll take questions. Yeah.
So any question for this talk?
Did you compare against AugBoost and not just like IJBM?
Yeah, so it's an important and interesting question. There's both AugBoost and CatBoost. So I'll begin with the original version of the paper. We only compared it in gradient boosting because the scikit-learn implementation, because the whole point is to improve on a given technique, and we think that the fair comparison to AugBoost would be to apply it on the code base of AugBoost. But I can tell you that I did an initial comparison also with AugBoost and CatBoost, and there wasn't statistical significance. But I think what was mainly interesting for us was to see that it was better than at least one of the libraries, which is considered state-of-the-art superior. IJBM is also one of the winners of many Kaggle competitions, let's say.
Any more questions? So I have a small question about the AAM-based example methods. So have you tried to change the model in an end-to-end manner?
No, we are with that.
End-to-end. That means you take the gradient and you propagate to the artificial neural network. Have you tried to do that?
So I can tell you, as the results we compared just to a regular neural network of the same type of architecture was much less good. but getting, I'd have to, I think, talk to you about the specifics of how you would see it work end to end. But I think a lot of the benefits of this algorithm, at least for the case of gradient boosting decision trees, is some of the special properties of decision trees. And decision trees don't use this type of back propagation. Decision trees, let's say, a special property of decision trees is that they train on a subset of a subset of the model compares on a subset of the samples, and that's very good for when you isolate the what didn't work well. And if it would all be like one big neural network, then I think you have a much higher chance of later on, kind of, if you fix what you're not good at, then messing up what you already learned in previous iterations. But I mean, if you have an interesting idea, I'd like to discuss.
Thanks. Next, thanks to the speaker again. So